a bit about me. I'm Anton. I've been working as a systems engineer for a long time. I tried working as a project manager at a game development company for about a year. Didn't work particularly well. I'm originally from Ukraine. I've been living there most of my life. About 7 years ago, I moved to Dublin to work at a big American corporation that wasn't Google. So the point number 3 is sort of the size of the companies I worked for, and you can see that it was mostly like small shops. Sometimes I was one of 5. Then 4,000 people was the company I worked for in Dublin. And then in 2014, I moved to London to work for Google SRE. I'm now part of Google Cloud, but I used to work on some ads products initially when I joined. I don't know if you know about Google SRE. We have probably one of the largest SRE organizations in the UK. We're about 240 people now. So there's many people working on like 20 different teams across cloud and ads and mobile and stuff like that. So site reliability engineering started at Google around 2003 as a separate team tasked with running production systems. And the team grew into an organization of about 2,500 people, which is a completely separate organization from product development org. And we're now a pretty big team, but over these 15, 16 years, we've been able to distill some practices and principles of how to run reliable systems. So even if you don't have a separate SRE team, you can use some of these principles yourself. So in this talk, I'm going to cover 4 areas. One is what SRE actually is and what problem it's trying to solve. Then we'll talk about the key principles of SRE, really just one key principle that kind of it's at the core of SRE practice. Then I'll cover very quickly multiple areas of responsibility and the practices of SRE, which means like what are we actually doing day to day. And finally, I'll summarize kind of the essentials of SRE and discuss how you could start doing this yourself. Let's start with like what is SRE and what problem it's trying to solve. So software engineering historically has been focused on designing and building systems and not so much on running software after it's been built. But according to multiple studies, like the cost of actually running a software system after it's been built is sometimes more and sometimes significantly more than the cost of building a system in the first place. And organizations, they often invest a lot into hiring the best and the brightest software engineers, but don't care much about operations. So very, very often operations is kind of like somebody else's problem. And incentives are not aligned at all in this sort of system. So traditionally, operations was a separate job role. You've probably heard about this proverbial wall where developers write some code and then they throw it over the wall to operators. And operations team would be responsible for running the system. And they will deploy and run it and maybe respond to events and breakages and fix some problems. And this results in a pretty antagonistic relationship between the two teams, right? Because they have very different incentives. Developers are interested in changing things and writing features and getting those features in front of customers as quickly as possible. And the operations team is mostly interested in not being woken up at 3 a.m. when something breaks. So most incidents, as we found at Google, are at least most of our incidents, let me say that, are caused by change. So the operations team is very incentivized to limit the rate of change. So in practice, this results in some sort of launch review procedures and difficult checklists on how you can actually change the system. And the goal of those procedures is they're basically trying to assess the risk of a given change, right? If you have a new release, you might be doing some mental exercise trying to assess whether it's a risky change or not. This doesn't work really well because operators are historically, they don't know the code as well as the developers, right? Because they're not working with the code directly, they're just running the system. So the group that is the most interested in assessing the risk of a given change is the least equipped to do so because they don't have as much experience with the code. Well, developers who wrote the code, they're not really interested in assessing the risk because they just want to get this out of the door. So the system doesn't scale very well. It's brittle. There are some techniques of how to deal with it, right? The agile practices, many people have heard about agile probably. And it's kind of, agile is designed to break that silo between development and business and product. But breaking just that barrier is probably insufficient, and this is where DevOps comes in and is trying to address the second wall between development and operations. So DevOps. There are many definitions of DevOps. I'm going to just pick one. And the one I'm going to pick is that DevOps is a set of principles that are designed to break down those silos between development and operations. And these principles have basically 5 key areas. First is break down that wall between dev and ops, help everybody collaborate and build and run the system more efficiently. Then we kind of know that things are going to break, so we might as well be prepared for it and accept failure as normal, because it's going to happen. Then smaller changes are easier to write, easier to test, easier to deploy, and what's more important, easier to roll back. So smaller changes help us run the system more reliably, because they make the incidents usually faster, incidents shorter, because you can roll back a change easily. Then we want to remove the human error as much as possible. So that means using tooling and automation to do things that would otherwise be done manually. And finally, measuring everything, or at least those four areas is very important, because you can't really improve what you don't measure. So throughout the rest of this presentation, I'll try to refer to these areas and kind of point out how SRE is doing a very similar set of things. And both SRE and DevOps, they appeared with the same goal of running large systems reliably, but they're kind of using the similar techniques to do that, but they evolve independently. So SRE approach is really based on 2 principles. First is that we use data to quantify reliability and make decisions about it. And second is that we treat operations as a software engineering problem, which means hiring people who can read and write code to do operations, heavily using automation, and making systems more reliable from the start, when they're being designed and built, not when they're already built and just we need to run them. So what we do in practice is that we develop software and procedures on how to design, build, and run systems reliably. We develop these engineering approaches that are used by other teams, not just by SREs, because many services at Google are supported by development teams and don't have SREs. We guide system architecture. We also are an operations team as well, so we're on call. We get paged when something breaks, and we're going to talk about that as well. So even though SRE started as a distinct job role, it's these set of practices and principles, they align pretty well with DevOps. So you can think of SRE as sort of a very specific implementation of DevOps principles. So the key principle that I'm going to talk about is error budgets. And if you're looking for one thing that distinguishes SRE from any other way to do software operations, it's error budgets. So as I mentioned, we're all about quantifying reliability and trying to make data-driven decisions about it. And the first question is obviously how do you measure reliability? And the naive approach is to measure uptime, right? You can count the amount of time that the system was working, divide that by the total duration of your time period, and then you get this fraction of the time your system was up. It's pretty intuitive for humans to measure, especially it's pretty intuitive for humans to reason about. And it's easy to measure if you have a single box doing things. As soon as you have a distributed system where there is multiple components, you have 10 servers, 3 of which are down, is your system up and down? And then if everything is down but nobody's sending any requests, does it matter? So very often you need to measure something different. A better way to think about reliability is measuring a fraction of good interactions over the total number of interactions. And here it's kind of specific to your system. Maybe if you have a web server, it's your incoming HTTP requests and the amount to which that you responded with a reasonable response. It's not a 500 error. It doesn't have size of 0. It's actually what the user wanted. And this is the way we measure is specific to a system, but what's important is that you should have a definition of what reliability means for your system. In any way, however you measure it, you need to set a target, right? You need to decide how reliable you want to be. And you've probably heard about 3 nines and 4 nines services, and it's really about the amount of downtime you're willing to tolerate if you can aim for like 3 nines, which is 99.9% reliable, it allows your system to be down for 43 minutes every 30 days. 4 nines give you this allowed downtime of only 4 minutes. So for 5 nines, you can only be down for 26 seconds a month. But it's not just counting time when your system is fully down, right? Outages don't always affect 100% of the system. And there is more nuance if you can measure partial outages. For example, in this case, if you're doing 3.5 nines, which is 21 minutes of total downtime, if you're only 1% broken, you can actually be in that state for 36 hours, right? Until you exhausted this unreliability window. So whatever target you choose, don't only think about the full outage, that the full downtime that your system is completely down, but think about what budget you have for a partial outage. There is one number that's notably missing here, and that number is 100%. And 100% is it might be a very intuitive target, but as Ben says, it's the wrong target, and we should believe Ben because Ben is actually the one who started the whole SRE thing at Google, so he knows something about reliability. So the reasons why 100% is the wrong number, well, obviously it's impossible, right? We cannot really guarantee total absence of failures. Then even if you try, it's the closer you get to 100%, the more expensive it is, right? And it's not just about buying more computers and putting them in different locations so they fail independently. It's actually about running your operations as a set of practices, right? For example, Google services like Search or Gmail have a very high target for reliability, and they have SRE teams in 2 different locations who have an on-call rotation, and they need to respond within 5 minutes when something breaks. And these teams do weekly reliability exercises and incident response exercises. They invest heavily in playbooks. This stuff is expensive. Like if you don't need to run a very reliable system, you shouldn't. Then the closer you get to 100%, the harder it is to change the system, right? As I mentioned, at Google at least, we found that most of our outages are caused by a binary or a configuration change, which means that the easiest way to make a system more reliable is to not change it. But that kind of is at odds with running a business because your customers probably want new features and that involves changing the system. And finally, the reason why 100% is the wrong number is that your customers probably will not notice after some point, right? If you're providing a web service, your customers probably use laptops or phones to access it. Laptops and phones are not 100% reliable. My phone barely works 9 times out of 10. Internet is not reliable at all. Like BGP routing gets reconfigured, DNS servers go down, like somebody digs fiber out of the ground. Like you just need to be significantly more reliable than this infrastructure between your users and your service. And then any errors that happen, users will attribute to the infrastructure, not to you. So we call this a rule of additional 9. Like if your infrastructure is 99.9%, you can run a 4.9 service and users will not notice. So realization that 100% is not the right target leads us to the concept of error budgets. And the basic principle is simple. Like you need to set a target that is less than 100% of how reliable your system needs to be. And it's interesting that setting this target is not a technical decision. Like I, as an engineer, I'm not making this decision because it's really a product decision. And it's based on customers' expectations. It's based on this infrastructure between you and the customer. It's based on your competitors and the reliability that they have. It can also change. Like if you're a startup and you're just providing a service that's not super important and you might be the only player on the market, you can be pretty unreliable, right? But if you're running a system in a highly regulated industry like airlines or banking, you need to be much more reliable because there are different expectations in that business, right? If you remember Twitter, like 10 years ago, you used to see the fail whale every other day because they were down all the time. And nobody cared. Like people are still using Twitter, right? Because there was no alternative. So the target needs to be set at a point where if you barely meet it, most of your customers should still be happy, right? So if you fail, like, for example, more practical example, right? If you set yourself a target of 99.9% and your system processes 1 million requests per day, you can fail 1,000 requests every day. And this is your budget that you can work with, right? And you can measure, you could use a monitoring system to measure the difference between your actual performance and this target. You know specific budget of how many requests you can fail. And then like any other budget, you can spend it. Like you can, if you see that you have a lot of error budget left all the time, maybe you're investing too much in reliability. Maybe you can run your system on a cheaper infrastructure. Maybe you can take more risks, push more releases. But if you run out of error budget, then by definition, it means that your customers might be getting unhappy, right? You've exposed them to unreliability to such extent that they might be getting angry. And in that case, you need to do something. And what we say you need to do is two things. First is decrease risk. So this usually means stop making changes, right? If you had a big outage, you probably shouldn't push a big and risky release the day after. And then invest your engineering time in reliability rather than features. The way we do that at Google is we freeze releases. When systems run out of error budget, we enter them into a feature freeze, which means you can't push new functional changes for some time. And that kind of achieves both. From one point of view, you're decreasing risk for sure because you're not making any changes. And then the engineers are kind of spending that time when the system is frozen on reliability fixes rather than on features, mostly to not run out of error budget in the future. It's a very big hammer, freezing changes. Very few companies, especially smaller companies, can afford to do that. But if you're going to use this principle, you need to come up with something that works for your organization. Something that when you're not as reliable as you think you should be, you need to change the way you do things, like decrease the amount of risk and improve reliability. So this system has a lot of benefits. First is it really aligns incentives between development and operations. Instead of fighting on agility versus stability and trying to assess the risk of changes, everybody works to the same target. Both development and operations, they know that this target is set by product managers. We agreed that we need to build and run a system to meet that target. And you don't need to assess any individual change. As soon as you have error budget, you can do whatever you want. When you've exhausted your error budget, you need to do something to increase reliability. You can make informed trade-offs between reliability and feature work, as I mentioned, right? If you have error budget left, maybe you shouldn't care about reliability until you exhaust it. Then you can use the system to evaluate multiple projects on how to improve reliability. Like if you have a choice between implementing gradual rollouts and canarying and maybe running your system in two different regions, you can calculate what will give you more error budget, basically, what will make your system more reliable for a cost, and then compare these two projects. So let's talk about specific terms. SLI that's one thing that you measure. It's your metric that is a proxy for user happiness. It's a metric that says how reliable you are. It's something you can put on a graph, and if it stays within the same bound, your system is working. If it goes down, something's wrong. The SLO is a specific target, which is at 99% or 99.9% over a pretty long window, usually like 30 days or even a quarter. And then in many cases, you'll hear the term SLA. That's much more common than the terms SLI and SLO. And what we at Google at least tend to mean by SLA is that it's your SLO that has some consequences attached to it. And in SRE, we typically don't think too much about SLAs. First, because SLAs are usually written by lawyers, not by engineers, and they are specifically designed in a way that the vendor almost never breaks them. There's one key difference also between your SLO, at least from the engineering product point of view, like the top sort of the topic of this talk, and SLA as a method of making sure that you hold yourself to at least some standard, right? Because SLA is when you give your customers their money back. You made them so angry that you have to pay them back. So your SLO, as I mentioned, should be set at a point where your customers are still kind of happy. Like if you barely meet your SLO, your customers, some of them might be getting grumpy, but they can still do whatever they want to do. Your SLA is set at a point where nothing works. They're angry, they're banging on your door. And there's a big gap usually between these 2 points, even if you're the same SLI. So what we tend to use for services that do have external SLAs is that we'll use similar SLI, but we'll set an internal SLA point at a much stricter standard, right? So one of the reasons to have these internal SLOs is that when you breach them, you have a feedback loop in your engineering processes that makes sure you don't degrade as much as to breach your external SLA. As I mentioned, when you fail to meet your internal SLO, you might freeze releases, invest in reliability, and one of the reasons is so that you don't go as far as breaching your SLA. As I mentioned, naive approach is to measure time. A better approach is to measure events. And you can use this both for availability SLOs and for latency SLOs. For example, an availability SLO would be something like 99.9% over 30 days. 99.9% of incoming HTTP requests over 30 days should succeed. And then your definition of succeed could be arbitrarily complex, but it's something that you can measure using a monitoring system. For latency, you could choose something like 95% of requests are fast, and then your fast is some latency threshold. If you miss your SLO, your customers are unhappy, you should do something. But it's also quite interesting that significantly exceeding your SLO is not very great either. Because first, it might mean that you're spending too much resources on reliability. Second, your customers might be getting a level of service that you're not really committed to guaranteeing them long term, and they will get used to it. So what we find specifically for these like internal services that are used by other teams is that when they have an SLO, it's valuable to enforce that SLO and to achieve that target, but not overperform it by much. And internally for infrastructure services, we have some teams that take their system down occasionally so that they barely meet their SLO, and their customers know what level of reliability they can do. Because you can overachieve your SLO by luck, month over month over month, but then some risk that has a very long time between failures, we're going to hit it, and you're going to go down for 2 hours, and then you've missed your error budget for years, basically. So overachieving your SLO is also quite kind of risky. It's really easy when you hear about the system is to try to come up with really good SLIs and SLOs. Like you think, I'm trying to measure user experience. I need to have a very complex SLI and have this SLO target that's very sophisticated. We recommend to not do that and start simple. And then basically every outage you have is an opportunity to revise these things. Because you can put a lot of thinking into measuring your SLIs very close to the user in a very clean and way that reflects user experience really well, but you're going to spend a lot of time doing that, and while you're doing that, you have no SLIs at all. And in many cases, just measuring for an HTTP service, measuring 500 errors on a load balancer and setting a threshold for that as a reliability is good enough. So if you have an SLO and you have an outage, then basically every outage you can compare. If you missed your SLO and your customers weren't happy, everything's working as intended. If you missed your SLO but nobody complained, then maybe you're measuring the wrong thing, or you set yourself a standard that's too strict. Or maybe you had an outage and you had customers complaining to you, but your SLO is fine. It probably means you're again measuring the wrong thing, or you set yourself an SLO that's too loose. A big question here is obviously how to measure user experience directly, and it depends on the system that you're running. For a consumer service, you can get feedback reports and you can measure. Surprisingly, setting up a search on Twitter for your company name yields pretty good results when users are getting angry. And I know at least 2 big American corporations that actually use this as part of alerting, but as part of Signal, maybe not directly alerting. So it's really useful. So to summarize, SLO is the target that is set by product managers but agreed by engineering that we can build and run a system to this standard. And it sets your internal expectations on how reliable your system should be. It should be documented. Everybody should agree what exactly you're doing if you miss your SLO, and what sort of actions you'll take to make your system more reliable in the future if you miss it. So as Agile focused on the wall between business and development, DevOps is kind of focusing on this wall between development operations. We think that SLOs are kind of bring all three groups together because they have the same incentives, they have the same expectations about reliability of the system. So it's on these 5 key areas of DevOps. You can see that SLOs, they align the 3 groups, so they reduce the silos. Everybody feels shared ownership about reliability, and there is no fighting between development and operations. Error budgets make failure normal. Like you actually codify the amount of failure that you think is okay in your error budget. So this aligns with one of the DevOps things. And then for this to work well, you really need to measure your reliability, and this means investing into your measuring your SLIs. All right, so I've talked about SLOs and error budgets. I'm gonna very quickly jump through a bunch of specific practices that we do in SRE and how we use SLOs in each of them. So I'm gonna cover 4 different areas that SREs at Google are responsible for, which is metrics and monitoring, capacity planning, change management, and emergency response. And I'll talk a bit about culture. So monitoring is a very important area for us. And it's because you, as I mentioned, you can't really improve what you don't measure. And we think that measuring reliability is very important. So we actually use a time series database internally. We collect metrics from all the services that we run. We use metrics as the main monitoring signal. Our approach to alerting is quite simple. We mostly configure alerts based on SLOs. There are two different notification mechanisms that we use. So we page a human, which basically means an urgent notification. You could be woken up if you receive that when error budgets are being spent very quickly. Like if you have this SLO target for your month and you're serving errors at a rate that you know will make you exceed your error budget in a matter of hours, you need to wake somebody up. Like the system is so broken that you will miss your long-term target for reliability. You need to wake up an engineer now. They need to be able to fix it. But if you just have an increased error rate, right? If your target is at 99% and you're serving 1% errors, so you're like exactly at your SLO, then 30 days later you will exhaust all of your error budget. But currently it's not an urgent problem. Like you can, if you think that your customers will be happy with 99% errors, 99% reliability, right? Maybe it's an automatic system that does retries, so like they retry 10 times. So those errors are not really visible to your customers. Then you don't need to wake anybody up for 1% errors. You can create a ticket. They can come to work the next business day, take a cup of coffee, and start. They're going to look at this problem in a matter of days, but there is no point in waking them up in the middle of the night. So we call this basically alerting based on error budget burn, which means how quickly are you burning your error budget. And if it puts your long-term compliance with your SLO at risk, but it's not urgent, like if it doesn't need to be fixed in a matter of hours, you don't need to wake anybody up. And a lot of teams only have SLO-based alerting, or at least that's sort of like a standard we strive for. We do have other types of alerts, more notably capacity alerts. Like if you think you're gonna run out of quota, probably you should get a notification before you do that, rather than when your system breaks completely. But in many cases, SLOs are the primary mechanisms on how we determine whether we should wake somebody up or not. Second area is capacity planning. So we want to avoid outages if more people are using our systems. That kind of makes sense. And historically, Google services grew quite a lot. So we invest heavily in understanding the demand for each service in each geographical location and making sure we have enough capacity in those locations to serve that demand. The other side of capacity planning is efficiency and performance, right? It doesn't make sense to run your system over provisioned by 10x when you have like 90% of your resources idle just to serve user requests faster, right? And similarly, it doesn't make sense to run your system at 110% utilization when you see saturation of resources and latency increase and customers are getting unhappy. So there is a point in between where you're utilizing your compute resources efficiently. And that's what we focus on in SRE as well. One of the managers in our team, he says that the mission of SRE is to run a system so that it meets its SLO at an optimal cost, which means if we're not meeting our SLO, we invest in engineering projects to make the system more reliable. If we do meet our SLO, we invest in engineering projects to do the same at a lower cost. That's basically, we always have stuff to do, either make it more reliable or make it as reliable as it is, but cheaper. It's not universally true, but it's a nice sort of framework to look at this. Like if you're meeting your SLO already, you should find other more impactful projects to spend time on. Change management. Yeah, this actually has the actual number. 70% of our outages are due to a binary or a configuration change. So the easiest way to run reliable systems is to not change it. So the purpose of SLO is kind of to maintain this optimal velocity while still meeting reliability requirements. So managing this risk introduced by change is very important. And if you think about outages, the impact of an outage is a product of its outage's scope and outage's duration, right? The scope is how big of a proportion of your service the outage affects. If you run your system in 5 different regions, being down globally is a bigger scope of a problem than only being down in Asia. So we decrease scope by doing gradual rollouts and canarying and doing experiments one failure domain at a time and introducing those failure domains in the first place. And then duration is we try to decrease it by making sure we detect problems as quickly as possible, and we have a very well understood set of mitigation steps. Like when something goes down, we know what to do. And that usually means rollbacks that actually work, or because each failure domain is independent and we usually introduce changes one failure domain at a time, maybe one region at a time, we can just remove live traffic from a region that's broken. Very often the problems we see in practice only affect one region. So instead of rolling back, that might take, 10 minutes. You can just stop sending traffic there. That takes seconds. And that already mitigates the problem. By the way, you could totally not have any pre-production environment and make changes on a live system if your SLO is very loose. Like if you only need to be up 90% of the time, then you can go and change your files on the production server manually, because if something breaks, you're going to notice it and do Control Z, Control Z, Control Z, and it's going to be fine. And you'll have enough time to do that. When you're running at 5 nines and you have 26 seconds of full downtime per month, you can't really do that. So this is when you need to do failure domains and testing and stuff. But if you have a very loose availability requirements, I would not have any pre-production environment at all. It's very expensive, and building all of that, testing, and no, this is the point of the whole system, right? If you can afford to not be very reliable, don't spend time. So again, when you have SLOs, if your target is less than 100%, then 0 outages is not the goal. The goal is to have many outages, but short and small, so that they don't affect a lot of your users and they last as quickly as possible, so they don't consume a lot of your error budget. Making outages faster requires quick detection of problems. And as I mentioned, we do alerting based on SLOs. Engineering SRE teams, they get paged by monitoring system directly. There is nobody who's watching drafts 24/7. We don't have a separate knock. People who know how to fix a system will get paged by monitoring directly. And engineers who are getting paged, they need to be able to investigate and at least mitigate the problem very quickly, potentially in a sleepy condition. So we invest a lot in good alert documentation and mitigation procedures that are tested and documented, so that even if you get woken up at 3 a.m. in the morning because all Asia is on fire, all of your system is in Asia is on fire, it's pretty easy for you to go and read the alert and copy paste the command and run it, or maybe you know the command already because it's so simple. We also do these regular incident response exercises. As I mentioned, many teams do them once per week, where we would pretend there is an outage. It's like a game, like an RPG. within a team. Somebody will pretend to be a monitoring system, the other person will pretend to be on call, and then they would describe a scenario when something went down, and whoever is pretending to be on call will try to fix it, but they will need to, they don't have a computer, so they need to talk through what they're doing, and the rest of the team are sitting there in the room taking notes, and it's a really good way to spread these troubleshooting techniques, like these funky shell scripts somebody has in their bin folder that fixes everything magically that they don't share with the rest of the team, or like monitoring dashboards that only one person knew existed. So it's a really nice way to spread this knowledge. And also you can talk through things like, oh, is this significant enough to declare an incident? And then you kind of teach and align on incident response principles as well. So when incidents do happen, we document them in postmortem documents. And as I just mentioned, it's really useful to have a clear definition of what an incident is. And our definition is roughly the one that's on a slide. And the first point here, the user visible downtime or declaration or degradation beyond the central threshold, that is derived from the SLO directly. So you know if you're consuming your error budget very quickly, there is a specific threshold after which you'll consider it an incident, and you'll write a postmortem document. And in the industry, we now call them retrospectives or incident reports. At Google, we've traditionally called them postmortems, even though it's not the best term. And the the point is to identify contributing causes and list action items that will either in the future make this less likely to repeat, or have this smaller impact, or be faster to mitigate. Right. So you want to. We're not afraid of outages, but we want to be in the novel outage business. Nobody wants to fix the same incident twice. So this is not a punishment, but a learning exercise. And making postmortems blameless is very important. I think this has been discussed in the industry quite significantly. But I'll repeat that even if the outage is caused by a human action, the point is not to call out a specific individual for making a mistake, but to understand what made that mistake possible. And we find that engineers are usually well-intentioned and they're trying to do a good job. And you've hired probably well-intentioned and competent person in the first place. So if a well-intentioned and competent person made a mistake, it's not their fault. It's a problem with the system and the procedures that make that mistake possible. And we have a culture, and I think it's really important to have a culture that allows people to admit they made mistakes. Because if you don't have that, then people hide their actions. And if a given incident is caused by somebody's action, you want that person. The incident will be resolved faster if that person tells you upfront that they've caused it, rather than if they hide their actions and somebody else is trying to investigate what's going on. One of the last areas I'm going to talk about is kind of on a cultural side, and it's about ability of SREs to regulate their own workload. So we are both an engineering team and an operations team. So it means we do have some amount of operational work, and it's usually something that you do manually to keep the system running. And we call this work toil. It's usually repetitive and automatable. And we find it's very important to manage the amount of toil that you have. You don't want the amount of toil to be zero, because doing these things manually makes you learn about the system and understand what to automate in the first place. But then you don't want the amount of such work to be large, because the volume of toil usually grows linearly with the amount of traffic, with the size of your service. So the more successful you get, the more work you have. And you can go into what we call ops overload, when a team just doesn't have time to do any engineering projects because they're fighting with this manual work. So we find we have a strict target of 50%. So an SRE team is not supposed to spend more than 50% time on this sort of repetitive work. In practice, we find that healthy teams spend maximum 25 to 30%. And that includes being on call, responding to tickets, writing postmortem. So it's everything that's not actual software engineering or designing systems and stuff. So as I mentioned, if you're going to treat operations as a software engineering problem, you need to hire people who can write code. we actually find that it works really well if you hire roughly 50-50 split of people with software engineering background and people with systems engineering or networking background. And this doesn't impact at all how we assign work within the team. Everybody writes code, everybody does the same set of tasks, but this diversity of backgrounds allows people to help each other in areas when somebody might be more strong than the other. So in practice, you'll find some people get hired at Google as like SRE software engineer, and I myself as an SRE systems engineer. So we kind of do the same work, but have different backgrounds. Finally, it's super important, at least we found for us, it's very important to keep SRE independent from your product development organization and kind of in control of their own destiny. And we actually have 10 times fewer SREs than we have developers. So SRE is a scarce resource. And many services don't have SRE support. They are being run by the developer teams. But having this independence allows and empowers team to enforce the SLO, and not when we run out of SLO, we have confidence to say no, we're not as reliable as we want to be. We need to freeze releases or do whatever we agreed to do in the first place when we miss SLO. And also enforce the toil budget, so that when the SRE teams find that they spend more time on toil than they want to, or than the hard limit, they actually have an ability to push back some of that work back to developer teams. All right, so to recap these 4 areas that I mentioned: metrics and monitoring, talked about SLOs, about dashboards that help us troubleshoot problems quickly, on capacity planning, I mentioned how we'd like to understand the demand for a service initialization and make sure that the services are as efficient as they can be. On change management, we do gradual rollouts and canarying to limit the blast radius of outages. We do consult developers on designs, making sure that the systems are built in a reliable and a scalable way when they're being designed and written, not after. And we invest in automation to decrease the human mistakes. On emergency response, we do on-call, we do postmortems. And on the culture, I mentioned how SLOs align these engineering groups, developer and operations, and how we measure the amount of toil as well, making sure that we don't spend too much time on it. Going back to this slide on how SRE aligns with DevOps principles, you can see that SLOs, they provide this shared ownership. Error budgets and blameless postmortems, like we codify the amount of failure in the error budget, and incidents are learning opportunities using the postmortems. And then the gradual changes, again, gradual rollouts and canarying. And tooling and automation allows us to respond to incidents faster, and measuring toil, both toil and reliability is very important. Finally, Google has been doing it for 15 years, so the SRE practice kind of evolved as the company grew. So it can be difficult to understand how you can implement this in an already established organizations that might have different groups that fight with each other, or that don't have incentives aligned. And changing all of your organization at once is obviously very hard and probably impossible. So if you're looking to bootstrap an SRE team, like if you want a separate SRE team that is similar to how we do SRE at Google, what we recommend is you start with SLOs, because like the goal, like the mission of an SRE team is to defend the SLO. And as I mentioned, SLO is at the basis of decision making of all the actual practices that we do. Then hire people into your operations team that actually know how to write code, or upskill existing operators. And you can do both. You can make sure that your existing ops people learn how to code, and hire software engineers externally into the same team, because SREs need to be able to automate their job and focus on high priority projects. Also, hiring software engineers into operations team ensures this parity of respect between development and operations. And at Google, we find this quite useful. Like when you get hired as a software engineer at Google, you actually have a choice whether to work on product development or in SRE. So everybody, the compensation is aligned. Everybody in the development side that knows there are software engineers just like them working on the operations team. We are as competent and as we can be. Like, we are basically two groups. They have different priorities and different focus, but we can do each other's job if necessary. And that makes sure that SREs are empowered to enforce the SLOs and the toil budgets, and also ensures that there is no first and second class citizens like it often happens in more traditional organizations with operations teams. And finally, provide the feedback loop for self-regulation. Again, systems, this is what we call the nuclear option at Google, but if there is a system that SREs are responsible for that is just not meeting its SLO because it's not designed and built in a way to meet its SLO, or if it's producing a lot of these toil and operations work, SREs actually have a way to push back some of the toily work to development teams, or if the system is just not reliable as it needs to be, SREs have a choice of returning the pager back to development teams. And it's very rarely used. It's like kind of like this a feedback, a thing to keep incentives aligned and keep developers still cooperating with the SREs, because it's still two different teams. They report to different managers. There's still a lot of negotiation going on, but this very real risk that developers at some day will need to just be on call for the system themselves, even if they did have SRE support in the future, keeps groups working with each other and talking to each other. So you don't need to build 2,500 people organization from day one. We recommend starting with the one service that you run to this model. And then it's important to get support from your management so that the SREs, you can actually enforce the error budget, because that's the most important thing. Is when you run out of error budget, you need to change the way you do engineering for some time to decrease risk and improve reliability. And often it's very valuable to have somebody in your leadership team who believes in this and can back you up and support you. If you can make one service and one team work this way, then other parts of your organization might be interested and they might come for advice, and you can spread this, but don't try to like change your whole company on day one. I think this is my last slide, and it's kind of trying to pitch the idea that SRE is a good way to run systems on cloud, because cloud gives you this infinite scale, but you don't want the amount of operations work to scale linearly as well, because you don't have an infinite amount of operations people, just like you can run computers in the cloud. So you can actually use this to achieve the same with less engineering effort. And then you don't have to have this tension between development and operations. If you have a specific reliability target, everybody can have the same goals in mind and not fight too much.
Thank you.